at this or be part of this panel presentation on climate and risk. Very briefly, I'm at the Renaissance Computing Institute, which is more of a cyber infrastructure software research institute, but we have an Earth Data Sciences group. It's relatively small, but we think we're doing kind of cool and interesting things regarding informatics and data sciences as they apply to the earth sciences, and certainly climate falls in that category. So we're at UNC Chapel Hill, just down the street. So very, very briefly, I mean, I'm a coastal oceanographer and do a lot of things about having to do with hazards and risks associated with living on the coast, in particular flood insurance, which is a very practical way that a lot of the research in math and science, and certainly ultimately climate, will help to inform basically how we go about things like risk transfer. So there's a very interconnected system. It's affected by storms, hurricanes, waves. Flood insurance, flood level recurrence intervals is really kind of one of the big ways we try to categorize or quantify hazard levels, and then onto risks. But importantly, the coastal zone is frankly where 90-something% or more of the goods and services that we import, which is a lot, come through a port one way or the other. So it's kind of the focus, if you will, of a lot of transport activity that is basically responsible for holding up and driving our economy. So one of the things that we do is we try to characterize these risk levels for various things, including the National Flood Insurance Program. There's a couple of ways of defining risk, but usually it's some combination of hazards times consequences, and then sometimes you include vulnerability. I typically try to make it a little simpler, at least on myself, and think that risk ultimately is about decision making and being able to take action, information that's digestible for decision making. And arguably uncertainty quantification is important, but I can tell you from a lot of experience that people on the ground making decisions about things like insurance rates, or whether a community is going to buy into a federal flood insurance program, uncertainty is not the thing they're thinking about. They're really much more worried about how much is this going to cost me. So in the hazards context, this is largely in the natural sciences and engineering. We define these natural hazards or these events one way or the other. Consequences, one example of property damage loss, for example, during events. Here's one of the things that I have thought about and done some work on. This is actually from a 2010 paper. This is FEMA, National Flood Insurance Program's kind of operating budget integrated over the last 30 or so years. And so what you can see is that the little bars are the annual premiums minus claims. So basically profit, if you want to look at it that way, or net. The red line is the green line is the accumulated premiums minus claims. And over a very long period of time, I mean, things were largely fluctuating about zero. There's a little bit, the red is the operating deficit, basically. So for a long time, they've been in the red, but not too in the red. And then 2006 occurred, and that was Hurricane Katrina. So what happened is that then in 2005 occurred. In 2006, all the claims start really rolling in. They had to get bailed out by the Treasury. In fact, they're not probably ever really going to bail themselves out without making the insurance rates actuarially sound. And that's a very big uplift or big lift on the part of not only the federal government, but the communities that are having to buy into something like a flood insurance program. The coast's population, so why are risks increasing, even if you take out the climate change argument? Well, people are moving to the coast. So this is from the National Climate Assessment. This is population increases in the coastal zone, and basically it's all positive. This is over the last 40 years. So this has a lot of consequences to aging infrastructure and how it is that the structures in the coast can actually be supported over a longer period of time, longer than something like design lifetime. So projections of sea level rise are, this is not new data really. Without ice sheet melting along the North Carolina coast, no dots in North Carolina. That's got its own political issues associated with being in North Carolina, but up and down, sort of north and south of there seems to be consistency that there's a foot or two potential sea level rise. Well, you throw in the ice sheet melting, and we're talking about double that. North Carolina, however, we're okay. So the other way to look at this is that these are the flood levels at the 1% annual occurrence rate. And again, north and south of North Carolina, they're on the order of 3 to 6 feet. But if you look at what will happen to the return levels over a long period of time, certainly in the middle Georgia coast right there, which is the 100-year, at least in this assessment, becomes the 5 or 2-year, which is really scary when you start thinking about what we do and don't know about climate variability. So how do you plan for that? And the answer is that it's very, very hard. If you give someone a planning number that says, here's the water level, and here are the error bars, well, that's great. They kind of know what to do with that. But when you say it's 6 plus or minus 4 feet, they're like, well, we'll just wait. We'll wait until we get better information. And of course, from a practical standpoint, at least in the lifetime of policies and infrastructure on the coast, we may not get that far. We may not get enough information to make any better decisions. So among the many problems, ecology, saltwater intrusions into estuaries that are fundamentally changing the habitats that food sources live in and grow up in. Down here, hydrologic and water systems. One of the big issues that has nothing to do with the climate, but certainly drives a lot of the risk, is development patterns. So when you put in parking lots upstream, right, you fundamentally change the flood frequency distributions. So then on top of that, you add things like precipitation changes over a long period of time, over climate horizons, if you will, then that's a very big issue. There's a bunch of risk transfer is the one that I think a lot about through federal insurance pools, things like catastrophe bonds. So this was really more about a coastal perspective on some of the things that climate and climate sciences will impact one way or the other. Whether or not 100% of the population buys into it is a different question. So I'll stop with that and turn it over to actually my colleague at UNC. I'll leave that to Richard. Yep, okay.
Okay, thank you, Brian. So while I'm pulling up the next talk, I will introduce the next speaker, who is Wei Mei. Hope I pronounced your name correctly. Yes. And he is an assistant professor in the marine sciences. I nearly said machine science. In the marine sciences department at UNC. So let's see if we've got this correct. Good.
Good afternoon, everyone. So my name is Wei Mei, and Richard said I'm assistant professor at the Marine Science Department at UNC, and also I'm working with Brian in Coastal Resilience Center of Excellence at UNC also. And so my research basically is focused on the dynamics and the interactions between tropical cyclones and climate. So next, I'm going to give a brief introduction to one of my ongoing projects that is related to today's topic of discussion, that's climate and risk. And hopefully it will be helpful for today's discussion. So this project, of course, is in collaboration with Brian and also Rick. So, okay. So, so we are now looking at the variability and change in hurricane activity, and also look at their, try to assess their induced coastal hazards and risks. So it is well known that the atmosphere is quite chaotic in nature. So we expect the hurricanes, as expected, the hurricanes exhibit strong internal variability in almost every aspect. So next, I'm going to show you one example, use the hurricane tracks. So this figure shows the hurricane tracks in 2005 based on observations. So this black dot shows the genesis location of the hurricanes, and the black curve shows the tracks after their genesis. Okay. So this is from observations, and next, this the blue dots and the curve shows the genesis and genesis location and tracks of hurricanes simulated by model developed by Jeff Dill. So we can, oh sorry, I should mention that. So in elevations, basically we can see about like 5 hurricanes may landfall along the Gulf Coast of the U.S. And for this simulation by the kind model, we can see also there are like 5 hurricanes may landfall along the Gulf Coast of the U.S. So, and the simulation in this simulation, the result is quite similar to the elevations. But then, if we look at another simulation, we're showing us the red dots and the red curves, we can see quite different from the previous simulation and also from the elevations. There are only like 2 hurricanes may landfall along the Gulf Coast of the U.S. Okay. So this basically illustrates the internal variability in the hurricane activity. So to resolve this issue, we need to use large ensembles of the high-resolution climate simulations. And based on this large ensemble simulation, we can obtain like probabilistic changes in the hurricane activities, like tracks, landfall rate, and intensity and landfall. And also, of course, the genesis frequency and also their peak intensity. And these models are pretty skillful and skillful. Sorry. So this figure compares the simulated and observed hurricane number in the North Atlantic over past like 60 years. So if we look at the recent 4 decades, starting from 1970, we can see, the black curve shows the simulations with the gray shading shows the 1 standard deviation, and the red curve shows the elevations. We can see the model is pretty good in reproducing the observed variations in the hurricane number. And also, as a byproduct, we found that in early 15 years, like before 1966, when the satellite measurements were not available, it seems that the current best track data underestimate the hurricane numbers by 1 per year. Okay. And this figure shows compares the simulated and observed the hurricane intensity. I'm showing here the 95 percentiles of the TC peak intensity. And again, the model is not bad. I mean, it can capture the largely internal to decadal variability in the observed TC intensity, particularly in the low frequency time scales, we're showing as the C curves. So then we have pretty good confidence in the model simulations and use these large ensemble simulations. We can, as mentioned, we can get like probabilistic change in the hurricane activity. And then we can use this information combined with other models like the ASERC storm surge model, and also with sea level change, we can estimate the storm surge change in both the present and the future climate. That's, so I think this illustrates as in one way that how we can connect the large-scale climate change information to like a risk assessment. Yeah. Okay. Thank you so much.
Okay. Thank you. And once again, I will introduce the speaker while putting up the slides of the next speaker. So Slava Lyubchich is from the University of Maryland, and also, let me see, yours is a PDF, is it?
Yes.
And I will let him introduce himself in more detail, but there we go. There we are.
Thank you. Thanks, Richard. So I'm glad to be here and present parts and bits of several projects that we've developed together with Yulia Gel, who is here in the audience, student Oshim, with whom we jointly co-supervise, and climatologist Holly Kilborn from our lab, and other students who helped us to collect and pre-process the data. So I come from a different background than the previous 2 speakers. Originally from Russia, then I was a postdoc at University of Waterloo in Canada, and there are no hurricanes. But we were approached in Canada by a large insurance company who was concerned about rising frequency and intensity of rain events, because rain surpasses the damage caused by fire and theft to the home insurers. And compared to hurricanes, non-catastrophic rain events are not covered by reinsurance companies. So insurance companies bear the costs, and they have to come up with a solution what to do with the rising losses. So Toronto is also not subject to hurricanes. So what we had from the insurance company, we had a very good data set for 10 years. It was claim by claim data on house insurance. So we had information on the houses and whether they had losses or not, which date was that, etc. We collected precipitation observations for corresponding locations and corresponding times, and we used scenario forecasts or scenario projections from global climate models. But as a deviation, we went to Norway because they had pretty good ensemble of climate models downscaled to 0.11 degree resolution. And we used, and their data, their insurance data were actually publicly available, so we were able to try our methods on Norway as well. So we used, for example, 2 locations, or Trondelag on the Atlantic coast and Osvold on the southern Norway with the sea coast. We use different climate models. There are a few of them. And we came up with a method to compare tails and distributions of precipitation in the observed precipitation and in projected. I don't go into details of the methods, but we were able to plug into the so integrated change in the tails and would see the relative increase in the number of claims dependent on the model and scenario. And what we found that there is a general trend in increasing a number of claims. However, there is a huge variability. Like Brian said, there is like, sometimes we go up to 2 times or 6 times, we're not sure. And it also depends on the model, not that much on the scenario. And again, the RCP 4.5 scenario is like was said in the previous days, is if everything will be good and we will curb the greenhouse emissions, and RCP 8.5 is if we'll continue business as usual with rising emissions. So you can argue that, okay, we compare the observations with the model, which is like apples and oranges. So we tried a different approach. We did 3 scenarios of comparisons. We considered what if we fit the regression models basically on observations and compare with different things, I would say. So what if we fit, let me start again. What if we fit the regression models on observations, or we can fit them on the ERA interim forced climate model? So we have 2 ways of fitting the regression model, and then we can compare this to the future model. The future model, which is the same model that is forced with ERA interim observations. So we had 3 combinations for those scenarios, and whichever scenario we use, the numbers we came up, in this case for only 4 Canadian cities, they were very similar. So there is a general increase in the number of claims we expect to see, and the numbers were similar across the scenarios for comparisons. The next step we took was to look jointly at the number of claims and losses. This is an extra and more complicated step because there are many factors affecting the losses. It would be the cost of the house, the the insurance amount, etc., the losses that will be incurred by the insurance company. So we modeled jointly. So we used SVN to project change in the number of claims. In this case, it's one of the Canadian cities. And we did it by comparing the baseline period of 10 years with future 10-year periods. And then we used the projected number of claims as an input to another SVN model for the losses. And this was the projected number of, the projected loss relative to the baseline period. And if we compare scales, here we have 25 max, here we have 50 max for the losses, the percentage. So it allows us to devise that we will probably see a greater increase in the losses, and the average loss will also increase. So at this, I'll stop here for discussion.
Make sure I understood it correctly. You were saying the losses were greater than under RCP 8.5 than... You said they were greater under 4.5 than under 8.5?
Yes, it happens. It's very local.
Okay, well, maybe we can pick up that in the discussion later. Thank you. So the last speaker here is Hans Kaper, who is from Georgetown University, and he's the editor of Siam News, and he's also been very prominent in the Mathematics for Climate Earth sequence of activities. So I will introduce him to talk about food systems and food security. Are you do you want to use the walk around, or
I can
just
use
speak
this,
it up?
yeah.
Okay.
So thank you, Richard. One correction, my name is pronounced Kaper.
Oh, I'm sorry.
You're not the first one to make that mistake, and you probably won't be the last one either. So I'm an applied mathematician by training, and have spent most of my career at Argonne National Laboratory, which is a Department of Energy lab, where I studied mathematical problems related to energy. When I left Argonne, 2001, I joined the NSF as a program director for applied mathematics. And when I left the NSF in 2008, I joined Georgetown. And my interest in the last few years has been climate, mathematical problems related to climate. And more recently, I study what is called mathematics of planet Earth. And if you want to know what that is issues related to climate, climate change, effects of climate change on society, sustainability, resilience issues, and lately I've become interested in food systems. Now, why would a mathematician get interested in food systems? Of course, it's part of mathematics of planet Earth. Yes, thank you. Why is our food system worth our attention? Well, it's under stress. The major stress factor is the growth in the world's population. We are now at 6 billion, almost 7 billion. By 2050, we'll be over 9 billion. Think of it. That's a tremendous growth. Not only that, but we're trying to help developing countries reach a higher living standard. As a result, their consumption pattern changes. They go from nutrition poor to nutrition rich food products. So there is an increasing global demand on the food system. So we need to increase production. That means that we have to go to industrial production, which is already happening in the Americas and in part of Europe. The FAO, the Food and Agriculture Organization of the United Nations, predicts that we have to more than double our food production by 2050. So there's pressure. There are other factors that come in, apart from population growth and shifting consumption patterns, namely climate change, water stress. There's more demand than ever on our water supply, and there's a finite amount of it. People are prefer to live in cities for whatever reason, so urbanization is increasing, and by moving people from the country to the cities, you make it more complicated to supply them with adequate nutrition. Globalization. Food is produced in one part of the world and consumed at quite a different part of the world. It used to be local. Now it's global. So think of the transportation system that's involved and that's required to bring all this to bear. What we are seeing in Africa, Northern Africa at the moment, and the Middle East, is migration. Why do people migrate to Europe? They can't get jobs and they can't get food. So these are unpredictable factors that play a role that affect our food system. That's why we should be involved as mathematicians in our food system. Our food system is somewhat like a climate system. It is a complex system, has many components. All the components interact. Think of production, transportation, consumption. All these elements interact. We have some idea how they interact, but mostly very little data. There are feedback mechanisms. As I mentioned already, the consumption patterns change. So it's non-linear, clearly. And there are tremendous risks, uncertainties and risks. So what I want to show you in the next slide is a study that was done last year, essentially. It was Lloyd's of London that initiated it, and there was a US-UK task force on resilience of the global food supply chain to extreme events. Insurance companies are worried that there will be a sudden shock to the system of a size that we have never seen before, and they wanted to figure out, can we cope with that? How do we redistribute the risk? That's why Lloyd's of London was involved. So here's a picture. They do just like climate people do. They design a scenario, what if, and look at the outcome. It's not that they try to predict what will happen, they are looking at scenarios. So very similar to climate science. So here's a picture of a scenario that, on the next slide, I'll give the details. But here's a picture that was initiated, a scenario that was initiated by a climate phenomenon. Here it is. And so, El Nino. Suppose there is a very stronger than usual warm phase of El Nino. And El Nino, we all know, is in the Pacific, right? El Nino is sort of a driving force of our climate. So it affects the climate worldwide. Let's say, as a result, there will be flooding in the US, specifically the Mississippi and the Missouri rivers, and large fractions of land that are used for cultivation cannot be used. Crops get lost. Further around the world, there will be drought in India. Not unusual, but much worse than before, comparable to 2002. Torrential rainfall in other areas like Nepal, Bangladesh, parts of India, Pakistan, flooding and landslides as a consequence. All this is caused by the foregoing. Essentially, it's all caused indirectly by El Nino, and then you have these other consequences. Severe drought in Australia, as we've seen in the last few years, and Southeast Asia. And then there comes a biofactor in. There is a soybean rust that expands to South America. So even South America is not spared by this phenomenon. And it causes epidemics, diseases, and what have you. Now some crops are resistant, but there's a rust, UG99, which then gets blown across the Caucasus and further north. So you see all these phenomena are caused by one phenomenon, El Nino. What happens? Crops are destroyed, landslides, land cannot be restored easily. It takes years. So now you have to estimate how does this affect the world population and our food system? Well, here it is. Rice production falls by 7%, roughly. Maize production by 10%. Soybeans by 11%. And if you figure out the price, because of shortages, for example, rice will go up 5-fold. So people who can barely afford rice today are out. They cannot afford it anymore. And what do you get? Riots. Look at the bottom line. Riots in urban areas because those people cannot get food. The Middle East, North Africa, we're already seeing some of it, and Latin America. So most parts of the world are in trouble. In principle, 7%, 10%, 11% is not fatal. The trouble is that it happens all at once. It's cumulative. So even though the magnitude is within bounds, we know or the system roughly adapts to it and gets through. In this case, it is disaster. So the effect is obvious. There are humanitarian disasters. There are environmental disasters. There are economic disasters and social disasters. So food systems play an essential role. We have to understand the food system to guarantee or achieve somehow food security. And that's why mathematicians should be involved in it. And that's why food systems is an integral part of mathematics of planet Earth. Thank you.
Thank you. Okay, so I'm just going to take a minute to let our technician reposition the camera so that we're focused on we'd like to be focused on the panel rather than the podium. But what I'd like to do now, excuse me. Maybe I can just make a couple of opening remarks just to open up the discussion and then invite questions from the audience and, of course, questions from the panelists to each other. So I guess my perspective on this session is that we've been talking all week about climate models and climate data sets, and there's been quite a bit of discussion of extremes, and all four talks have in some way, in some respect, talked about extremes and their effect on the different kind of risks they were considering. I've always thought of this field as being sort of the applied side of climate science. There's been a lot this week about the fundamental science of climate science, but there's a whole other part of IPCC, which is Working Group 2, about impacts. And what we've been hearing is very much a matter of what are the impacts of changes in climate. So if I could pose some generic question to everybody in the room, including the panelists, it would be about how are the new technologies that we've been learning about this week relevant to the kinds of problems that we've just heard from our four panelists. So let me just pose that as one very generic question and invite either responses from the panel or further question or discussion from the audience. Who would like to go first?
I can say something in the context of food systems. So obviously there has been a big effort to do research in food systems. The U.S. Department of Agriculture has a research program. There is a group of people called AgMIP, which acts somewhat like the IPCC. There are lots of models. These models are usually black boxes. We don't quite know what's going on, and they're certainly not well coupled. It's essentially like the climate system, like climate science in the 80s, 70s, 80s, where you had an ocean and atmosphere model, and somehow you kludged them together and came up with a prediction, right? They have lots of models on different crops, on different regional areas, and our job, I think, is to look at the whole system and see whether we can somehow integrate some of these models, find out what the essential problems are, where the bottlenecks are, and use statistical methods, use applied mathematics methods to figure out how can we understand this system. At the moment, nobody understands the food system. And that's our job.
So I'm on the periphery of one of these NSF-funded, out of the social sciences, that does decision-making under uncertainty, called RIDSEP, Robust Decision-Making for Climate and Energy Policy. And I'm mostly on the climate side, but I get to see a little bit of the rest of it. And part of what we struggle with is to make the connection between the climate side and the impact side. So what do the impact people need as, for example, inputs to their models? And some of these models are very simple. They just use like the global mean temperature. Well, you don't need people running lots of GCMs or doing fancy analysis if that's the only input into your impact model. So we've really struggled with making meaningful links there from the things that we think we can maybe do from the climate side to how we can actually improve the impact side. So if we give them an ag model better resolution, or in either space or time, does that actually lead to more useful inferences about agricultural production, or is that not the weak link in the chain? So I'm wondering if some of you have experiences with either successes or problems with making that coupling.
Is there something?
Well, we had experience with inputs. We had problems with inputs. Like I said, from climate models, we didn't have enough spatial resolution. So we went to European domain because they had better spatial resolution for downscaled global climate models. And another thing is that models are not well calibrated. So they don't, if they match the mean, they don't match the quantiles as well as the mean. So when we are focusing on extremes, this is very important to have a well-calibrated climate model.
I'll go there and then.
So this is a question for Hans. So one of the things that I get to hear about food security is that it's a major problem of logistics, of supply chain rather than of production. And I guess logistics is actually something that is very much at risk from climate change. And well, you, but also the rest of the panelists, I guess, would you care to comment on or suggest things that SAMSI can do in the next year?
In the next year? Whoa.
Well, yeah, or the next decade. Feel free to choose your timescale.
Underline.
I'm trying to think of as concrete an example as I can come up with. Right now, food is transported all over the world. There are ships sailing from left to right, north to south, and somehow you would think this. People have an idea what is where. It's not the case. So an information system, you might say, is something that is more computer science than mathematics, but it's something that would be extremely useful. If a disruption happens somewhere, what is the effect? At this point, they cannot predict. There's no way. So a sort of a clickable, interactive information system about food and the logistics part of food system. That would be a useful thing. In my opinion, what I would like to see, and this is something for the working group to consider, is in climate science we have GCMs, we have intermediate complexity models, and we have conceptual models. And conceptual models, those are the ones I like, because I can say something about them, right? I use them to study particular phenomena that happen in the climate system. Something like that in the food system would be very useful too. So that's for those who like modeling and who want to come up with simple models that tell you, hey, here is a parameter that has a critical value. If you pass it, you go somewhere where you don't want to go. Conceptual models of the food system, that's one thing we could start working on.
Okay, thank you. I'll ask Julia and then Michael.
I would like just to add a little bit to the question about what end users need, those who work with impact. So I have talked a lot with insurance companies, and the question that reiterates again and again is how certain you are in those climate models. So because those people are doing the, really risk management. They need to know how they're going to price your insurance for your house, insurance for your car, and so on. So they need to incorporate uncertainty within their products. So that's extremely important to them. And so they have been asking again and again, so how certain you are that this climate model works here? And we don't have an answer. And when you show that examples like what Slava showed in Norway, it's like a whole range of outcomes, and all we can do there is just to provide some general trend. It's just saying that, I don't know, British Columbia coastal area going to be more affected versus than California, for example. That's it.
Okay, thank you. Michael. Oh, I'm sorry, I should have asked, does anybody on the panel want to respond to what Julia said? Apologies.
Well, I do in a sense. When I heard impacts, I was thinking more about the science of the impacts. You take a hazard and you force a social system somewhat academically, and maybe you construct some sort of complex systems model to try to model the behavior of that system. But when you get down to the end user, in other words, if that information were useful, how do you communicate it to? Insurance companies is one thing because they're chock full of PhDs, statistics and math and all kind of things. The part that I worry about is even at a level way below that, which is the insurance companies are going to make a decision. They're going to draw a map. They're going to say this is what the rate is, and then you're going to have a community who says no way. We're not about to pay that. So the recourse in that case in the flood insurance situation is that the community can self-insure, and if they do that, then they are very likely to underinsure themselves. Because as from a science perspective, I think we have a reasonable handle on what today's risk levels are. The real challenge is with development patterns and things that are happening on a much faster time scale than the evolution of climate science or the climate itself. We can't keep up with it. And so there's going to be a point at which there's a chronic underinsurance level that the reinsurance side is not going to be able to pick up, and that is where the impacts. That's the part that would worry me. And in North Carolina, it's a little bit acute just because of the politics, but just the communication of risk. Forget about the specific case. But we've had two hurricanes. One went to the north, to the south, and one went to the north. And the communities in the middle quite literally think that their risk is lower. And so that's the level at which. So we're all, this community here, it's a long way away from any of the results here that ever make it to that level. Part of that is that people don't want to hear it. Part of it is that it's complicated. So that's not an answer to the question. It's just more of an opinion about it.
I'd like to go back to the food issue. I've recently become interested in California agriculture and global warming's effect on that. And I'd always thought that in heat waves that the victims were the very old, the very young, and the very sick. In California, it turns out that it's mid-50s Latino males. And who are those people? They're undocumented farm workers who were out in the heat of the day. Even under the most optimistic of the Paris targets, in much of the developing nations in the low latitudes, especially the ones that are humid, it will be too hot to be out working on farms in the middle of the day. Can you comment on, what this community should do to help sound that alarm?
Stop denying climate change. That's the best advice I can give. As long as we are governed by people who have no idea about the science behind it, who don't want to believe the results of the science, it's hopeless. So we have to proselytize and make our findings known somehow, whatever way.
Well, you best to do that. I've been trying.
So have I. It's a cultural problem, right? People don't want to hear the bad news, and you have to start early in the educational system. For example, I come from a country where, I was born below sea level, right? If you think about this, so the Netherlands. There, as small kids, we were already taught how the system works, how we are protected by dikes against the sea. So for us, it was natural to, you know that a dike is not like this, a dike is like that. We all knew that. People here have no idea about that. And it's the same with climate change, temperature rise, 2 degrees, 2 degrees, what? Huh? It doesn't impress them. But if you tell them that there won't be food, there will be mass migration, it will hit your pocketbook, then they may be able to listen. So you have to start early, and you have to make it clear that it is a real problem. It's a global problem. It's not just our problem. It's a global problem. So together we have to find a way out.
I hear you. Too often, I think, at least myself, I've been afraid of being labeled an alarmist. But I think what you're saying is that we need to be alarmists.
Yeah. Well, the first industry that will be hurt by climate change is the insurance industry. So maybe it would behoove us to sort of talk to them, right? And convince them of what is coming if we don't do anything.
Then we'll go over that side. Sorry, Ben first, and then we'll go over that side.
Thanks. In the context of risk and impact, and I guess this is a sort of comment really for the group, the working group, as much as the panel. But you're wading straight into society and people and politics, and so that invokes communication. I mean, that's key, and therefore, presumably for that group, communication. Thinking about communication at least as part of the focus will be important. It seems to me. Just as a sort of follow-up to that brief interchange about how we communicate climate change, it has. So when I've been thinking about this lately, one thing that has frustrated me is that we've seen that the kinds of communication that we do as scientists, is be rigorous and communicate clearly is simply not working in the current world. Facts are seemingly irrelevant, and therefore, the onus is on us to be. We have the luxury of education, and most of us wealth, or some degree of wealth compared with the rest of the world. And we therefore should be able to communicate. Think about how to communicate in the most sensible way. Think about alternative ways. Apply our intelligence to that problem. Thinking about it perhaps in a different kind of way than rather than just trying to push out the message or be alarmist or any other very conventional kind of approach. Anyway, it's just a thought on that.
I just had a question regarding a lot of the analyses and approaches that we've been talking about this week. Do you think there's something fundamentally different in the way that we should be approaching the problem if the goal is risk mitigation versus risk transfer? That is, if it's a matter of design and policy, or if it's a matter of insurance. Are there different questions, different kinds of ways of thinking about the problem when you're focused on one or the other, or is everything relevant to each?
Well, I think that they go hand in hand. I mean, really, transfer and mitigation are related. We should be striving to not only mitigate the effects, whatever they may be, but also adapt to them. If you think about the coastal zone deciding overall to say, well, let's all move inland. Not only would that take 100 years or whatever the case, there's not enough money to do it. So you're going to have to do that risk transfer at some point. And as far as we're not going to stop this train from. You might be able to get a little bit of the way, not without both sides of it.
My question is more from the science. My question is more from the science side. Assuming the decision makers can reach an appropriate balance, given resources, should we be explicit in our work about thinking about whether it informs risk transfer or risk mitigation? In other words, are the ways in which we might address uncertainty, or the statistics we might use, or the scenarios we might run, or the scales that we might be assessing?
I personally think that the science is the science, right? I mean, we're going to do that, and we're going to do the best job that we can. We're going to characterize it in ways self-consistent. I think that the next step of getting it further out the door is really where we are. I don't know what the answer is. Maybe more experience, better opinion.
Well, looking back at my experience working with other scientists, right, which I've done all my life, there are ways we can do things differently, and we probably should. In this case, we have to use it to look at the end user. When we do our science, we have sort of a path ahead of us. We know where we want to go, and we don't really look beyond that. Maybe some of us, not everybody, some of us should begin to interact with the end user and figure out what they really want. It's a long process. It's not something that you sit down over coffee or tea. It takes months or years. But maybe we should motivate our research, the directions in which we are going, by what the user wants. We have not done that, not very well.
So I just wanted to jump in really quickly and tie together something that Michael said with also Yulia. Completely by coincidence, yesterday I was on a conference call with the Society of Actuaries, which is the largest North American insurance group, and it's about climate models and climate model projections. And there's some folks on the call who very much want exactly what Yulia just described, which is models which come with a sense of their own uncertainty in the predictions. And so that would be more useful to them. But what was interesting to me is there's other folks on the call who don't believe the models because they are not provided with a sense of their own uncertainty. They feel that they're just an average with a massive uncertainty in the future. And you show them the ensemble across CMIP, and they say, no, that's a lot of models, none of which come with their own measure of uncertainty. That's just 50 people making the same mistake. And so I actually think that providing measures of uncertainty would strengthen the science, be more useful for the users, and help the insurance industry and actuaries believe them. and use them in their results. And the thing to remember is in insurance, when you give them more uncertainty, that increases the risk. That makes the extremes more likely. That's what they want to see. They want to see these outcomes. And I really think more measures of uncertainty within a single model would go a long way towards providing that.
Can I just ask you a question to follow up on that, though? I mean,
sure.
do you have a sense of what measures of uncertainty the insurance industry would like to see?
Well, I think what it comes down to is, so you know that figure, one of the CMIP figures, there's something like 39 model runs into the future, and they provide an envelope. And the envelope is drawn as a shaded sort of box. What they want to know is that that envelope somehow represents the probability distribution they should be worried about, and it doesn't.
Right. Right.
It represents 39 or however many runs that scatter up and down, and you can draw into that envelope. So what they really want is a probability distribution at a future fixed point in time that they can then use to do sort of stress testing. The 1 in 100, the top percentile or the median and so forth. That's what they want.
Okay. Okay. Michael and then Chris Bretherton.
So we do have some resources for that. There's this large ensemble from the NCAR CESM, which has 40 simulations of the RCP 8.5 simulation. So you could make that same plot except for one model and 40 different initial conditions, and it does have quite a bit of spread in it, particularly when you get down to the regional level. Is that the kind of information you're talking about?
Well, yes, but that's all conditioned on the RCP 8.5, right? So they want it as well for the 4.5 and the 2.6, and they want the full range of the uncertainty there as well. Yeah.
I guess I want to respond to that and maybe bring up a separate point. So in response to that, I think the reason that we don't have those uncertainty bounds is that we don't actually know how to make them. I mean, these are obviously models which are composed of a lot of components interacting in complicated ways. So trying to estimate the model uncertainty by thinking about the component uncertainties is not a useful way to go. And we don't have the 21st century to tell us about the model uncertainty as a whole. I think those of us who work in the area probably would say that range, intermodel spread, probably is actually not a bad estimate of the model uncertainty. It hasn't changed much over time. The central value hasn't often gone outside the range from the previous intercomparison. So, there's a fair degree of robustness to it. So those of us in the field tend to think about that as a measure of uncertainty, even though we know it's not really. I guess the question I wanted to bring up had to do with the fact that, so a problem with global warming is that, there are winners and losers. And, I often hear the argument, well, there's winners and losers, and therefore maybe we shouldn't be too worried about it. But what the real problem is even if there are winners and losers, it's how much is lost by the losers that's really important. And I'm wondering whether you know of estimates of the economic costs of climate that try and estimate how much is lost by the losers versus gained by the winners, and whether those would be helpful to our arguments about the economic importance of climate change. And people should be more worried about it from that point of view than maybe they are.
It is somewhat unfortunate that political decisions are motivated by economics and not by science. Economics is not a science, as far as I can tell. I have a neighbor who is an economist who works at the IMF, at the International Monetary Fund, another neighbor who works at the World Bank, both economists, and they tell me, you can do your science, but the politicians will listen to us. So that's a frightening attitude, right? You come to think about it. And if we can change that even a little bit, we would be ahead. And society would be ahead. But how do you do that? I don't know. I talk to my neighbors and that's it, as far as I can go, right?
But maybe while we're talking about prediction from models, I can just interject the comment. There is a literature about using formal statistical methods, including Bayesian methods, in multimodal in characterizing uncertainty of multimodal ensembles, and that has been reflected in IPCC reports. So it's not a completely blank page. Chris at the back.
Thanks. Just a quick follow-up. I'm glad you made your comment about economics not being a science, because you just dissed a whole lot of social scientists who do consider what they do science. But that leads to my other point, which is a lot of the questions that are being talked about here could really benefit from having social scientists in the room who study this stuff and do models and all that good stuff. You know, human beings aren't rational decision makers. That's why, you know, the traditional formal modeling for microeconomics is going out the window, and they're doing things like behavioral economics. And it might be a nice complement to what's been done this week to maybe have some kind of a follow-up where you bring in a bunch of social scientists with all of us and work through some of these issues. One of my favorite things is to compare two diagrams that are out there. One is on Earth systems, you know, with all, you know, the atmospheric system, the oceanic land processes and so on. And then down here is a little teeny tiny box for the social processes. Well, then you go to the social diagram, which is for human dimensions of global environmental change. And in their diagram, the physical processes box is really tiny. So somehow those have to be brought together or aligned better. And maybe these kinds of, the expertise here might help that.
Okay, I think we take a couple more questions. We'll have one there and one from Hans.
So maybe just to add to the mix, there's a lot of focus on the politicians and changing their minds, but there are other avenues of approach and sometimes more effective, as in the business community. The insurance community doesn't have a luxury to play around with whether climate change is real or not. But for example, when we talk about information systems, and this is not to, let me say, this is a disclaimer, and I'm neither for or against this company, but for example, Walmart has a center for climate prediction, or weather prediction, excuse me, because they have an integrated supply chain, and they're very well aware of those issues, and maybe some of the focus could be shifted to these larger companies that are involved in the food chain, supply chain, and getting them involved, or even with the insurance companies, as they talk about their rate increases, letting their customers know why those rate increases are coming.
Comment?
This is less of a question, but maybe an observation. While the discussion about what we would call outreach, dissemination, working with decision makers was in the context of this working group and the panel, maybe it would be not such a bad idea if some of the other working groups also could check if there's maybe room for a bullet point on their list of topics. Not all of them, but some. How can one maybe disseminate, put a bit of an outreach and educational component into what we're doing here? It might find room in other areas also. Just to come up, not necessarily to make ourselves, to make our consciences, to assuage our consciences, but also maybe to come up with some ways of sharing some of the insights and bring them to people who are not as familiar with what we're doing here. It would perhaps be a good thing for all of us.
Okay, well, I'm not going to ask for closing speeches, but do any of you want to make a couple of remarks just to finish off in response to what Hans Engler said or anything else that was said earlier?
Join our working group on food systems.
Join our working group on coastal risks. No, I mean, I think we give a lot of lip service actually to things like outreach, and NSF proposals kind of require. The more we take it seriously, the better off. Realize it in the next 5 years.
I like to comment about approaching other companies. So far, we tried to approach the transportation authorities in Maryland, but about changing the building codes for infrastructure, but they didn't like the idea of climate change. So, and please join us at the Climate Informatics Workshop at Ankara.
Okay, well, let me thank all 4 panelists and everybody in the room for contributing to the discussion. Thank you very much.